Today we'll continue talking about the Sylow theorems. So we still haven't actually stated any of the Sylow theorems, but recall from last time that we stated the following proposition B, which was motivated by our understanding of how P groups act on sets whose cardinalities are co-prime to P. Okay, so this was a converse to that P group acting with fixed points proposition. So we had called it proposition B last time. So let me just recall the statement in the contrapositive form, which says, suppose I have a group G whose cardinality is divisible by P, but suppose G is not a P group. Okay, then you can construct a finite G set X such that P doesn't divide the cardinality of X and such that there are no fixed points. Okay, so this is in some sense a statement about the existence of fixed point free actions with also satisfying that cardinality co-prime to P condition. Okay, and these are the blanket assumptions. G and X are always finite. P is some fixed prime number. Okay, now this is going to somehow be our starting point for the first Sylow theorem. So let me state what is called Sylow theorem number 1. Sylow theorem 1. Okay, what does it say? It says let G be a finite group whose cardinality is divisible by P. So same assumption as above. So I will assume that the cardinality of G is of the form P power dm. So I'm assuming the cardinality is divisible by P. So I'll say D, the power D is at least 1, and here M is at least 1. Okay, so let G be a finite group whose cardinality is divisible by P. That's all this statement is saying. Then the Sylow theorem says that there exists a subgroup H such that cardinality of H is exactly P power D. So take the maximum power of P which divides the cardinality of the group, you can find a subgroup of that exact cardinality. Okay, so this celebrated theorem statement is called Sylow theorem number 1, and it will turn out that in some sense this statement here is actually equivalent to proposition B. Okay, so this is the in fact what we will talk about today. Okay, so I will at least establish one side of the equivalence and leave the other two. So let's prove the Sylow theorem. So we've already proved proposition B. Let's use proposition B to show how the first Sylow theorem follows. Okay, so let me proof of this Sylow theorem. So first observe that if G is already a P group, if G is a P group, what does that mean? It means that G, the cardinality is already a power of P. In other words, the number M is just 1. Then this is trivial. The assertion is trivial. I just take H to be G itself. Okay, and so the theorem is done. I mean, the proof is done. There's nothing to do. Okay, so done. Otherwise, in other words, if M is at least 2, or in other words, there are other primes which divide the cardinality of the group, then let's use proposition B. Okay, now we are in the setting of proposition B, which says that if a prime divides the cardinality of the group, but G is not a power of that prime, the cardinality of G is not a power of that prime, then I can manufacture a fixed point free action whose cardinality, or fixed point free action on a G set whose cardinality is not divisible by P. Okay, so otherwise, okay, so now let's use proposition B to conclude the following. Use proposition B, or let's write it as using proposition B by proposition B, there exists a G set X with two properties such that P doesn't divide the cardinality and there are no fixed points. Okay, now what does this get us? Here's the first observation. So suppose I have a set X on which the group acts. Recall that there are the action of the group splits this into equivalence classes, which are the different orbits. So let me just draw a picture. These are, let's say, the different orbits of the various elements. Okay, so I have my orbits. Okay, G orbits in X. Okay, that's what the picture is. Now observe that the sum of all these orbits, so let's give these orbits names, maybe O1, O2, dot dot dot, there are some finitely many of them. Observe that the sum of the orbit cardinalities is of course the cardinality of the whole set X. Okay, so this cardinality plus this plus this plus this plus this and so on is just going to give you the full cardinality. Now since the whole cardinality is not divisible by P, at least one of these OIs, there exists an orbit whose cardinality is not divisible by P. Right? Otherwise, if every single orbit had cardinality divisible by P, the total sum would also be divisible by P. Okay, so let's pick that orbit. So let's take an element in that orbit. Maybe, so in my picture, let's just say maybe this green fellow has cardinality which is not divisible by P. So I'll take this orbit and let me pick a particular element in this orbit. Okay, so let me take an element inside. So let me call that element something A. Okay, so let A belong to that orbit. So suppose, so let's say, so suppose A is that guy. Suppose the orbit of A, so this is, remember this is the notation, G dot A just means the orbit of A has the property that P doesn't divide the orbit cardinality. Okay, suppose the orbit of A has the property, you should say, has the property okay, so consider that particular orbit, the one that's marked in green there. Now let's recall the counting statement, which says that recall the counting theorem, which says that the cardinality of an orbit is just the cardinality of the full group divided by the cardinality of the stabilizer. Okay, so what is GA here? GA is nothing but the stabilizer of A, which just means it's all group elements G which fix A. Okay, so this is just the counting theorem. So what does this mean? So what is this GA here? So what are our conclusions? So here are various conclusions. Consider this new subgroup. So remember, the Sylow theorem says that we are trying to find a subgroup with some properties. Okay, so consider this subgroup GA. Okay, so this is sort of going to be my candidate for my Sylow subgroup, or my subgroup H, whose thing is a power of P. So let me call it H1. Consider the subgroup H1, which is the stabilizer of G. So this is a subgroup. Okay, so this is just my notation for now. I'm just calling GA as H1. What do I know about it? Okay, consider this. Now let me try and figure out some facts about it. First thing I know is that the cardinality of G by the cardinality of this stabilizer, so cardinality of G divided by cardinality of GA is the cardinality of the orbit, which is not divisible by P. That was our assumption. Okay, so now what does that mean? So let's write this cardinality of G as P to the D times M. Cardinality of GA will be some power of prime P to the D prime times some number M prime. Okay, so D prime is some power, so I don't know, could be 0 as well. m prime is some number which is 1 or more. Okay. Now let's divide cardinality of G by cardinality of GA. So observe, any number, any natural number can always be written in this form as p to the some power times some natural number. Okay, uniquely where p doesn't divide m prime. Okay, so this is p to the power d prime times m prime. Now in this quotient, what is it that I know? That finally there are no powers of p occurring. Okay, so after I consider this quotient here, after I have cancelled out all the common factors, what I know is that no p's occur, no powers of p are left over. No powers of p divide this quotient. Well, when can that happen? It can only happen if every power of p on the denominator, everything here cancelled out everything on top, right? Only then can you not have any p's remaining. So remember, m and m dash are relatively prime to p, right? They have no p's in them. They are products of powers of other primes. So what does this mean? This means that the only way this could have happened is if this power d prime was actually equal to this power d. Okay. In other words, what have we done? We have constructed a subgroup GA which has the following property, that its cardinality looks like this. It's p to the d times m dash. Okay, the d being the same d as what we had for the original group. Okay. Okay, so this subgroup, so maybe let me call this subgroup not as H1 but as H dash. Okay, so H dash is this subgroup here, and what I conclude is that H dash has, so it's just another name for GA. This is has cardinality which also looks like this, p to the d times m dash. Okay, for the same power p to the d, m dash, p doesn't divide m dash. Okay, now so we're almost there. In other words, H dash is almost the subgroup we are looking for. What is it that the Sylow theorem says? Here's a statement. It says that I can find a subgroup H of G whose cardinality is just p to the d. Okay, just that maximum power p to the d. This is an almost, so by the way, this such a subgroup H is called a Sylow subgroup or a p Sylow subgroup. What we have manufactured now is something which is almost a p Sylow subgroup. Its cardinality is, the maximum power of p is the same, it's still p to the d, but then there is some additional factor m dash here, okay, which could be 1 or more. If m dash is 1, then we are done. Okay, okay, so we are almost there. So this is see, so let me observe the following, that to start with I had my original group G whose cardinality was p to the d m dash, p to the d m. Now inside G I manufactured this GA subgroup which we will call H dash, whose cardinality is also the form p to the d times something. Okay. Now observe, this G is of course bigger than H dash. H dash is a subgroup of G. So observe certainly that m has to be greater than or equal to m dash. Okay, because the cardinality of H dash is less than or equal to the cardinality of G. Okay, but in fact this is strictly smaller. Okay, but observe something more. M is actually strictly bigger than m dash. Okay, in other words, this is a proper subgroup. This is not the whole guy, it's actually a proper subgroup. In other words, H dash can't be the whole thing. Okay, why not? Because if H dash, the subgroup we have constructed, is the whole group G, then it means that, well, what was H dash? It was the stabilizer of that element G. If the stabilizer of that element is the whole group, then that just means that every element of the group stabilizes that element A. In other words, the orbit of A is just the singleton A itself, right? or if you want to think in terms of cardinalities, the cardinality of the orbit is just 1. Okay, now what does that mean? It means A is a fixed point. Okay, but that's a contradiction. Remember, this was a fixed point free action. So that's why we're using that property, that since it was a fixed point free action, the subgroup, the stabilizer of that element A is a proper subgroup of the B group. Okay, so we have managed to sort of reduce the size of the problem. Instead of the original group G, we now have a proper subgroup H prime. Okay, and both G and H prime have the same power of P, the same highest power of P dividing both. Okay, now it's all we have to do is really repeat the argument. Now here's the next step. If H prime is a P group, if H prime is a P group, what does that mean? It means that power M prime is exactly 1. I'm sorry, the number M prime is 1. Let's go up again, which means that this is already just the cardinality is P to the D. Okay, there's no M prime in it. Then we are done. Then H prime itself is your Sylow group, right? Is the P Sylow subgroup because its cardinality is exactly P power D. Okay, then again we are done. Then take H, the P Sylow subgroup in the theorem, to just be H prime, and we can stop the proof right there. Okay, if not, well, then let's repeat the above set of arguments. Repeat the above arguments using proposition B. So remember, proposition B is really the key statement that we need. It says if you have a non-P group, then you can construct a nice fixed point free action. Okay, so if you see what we have done, if G is not a P group, it had cardinality P to the dm, and if M is not 1, it's not a P group, then we are able to construct a subgroup H prime whose cardinality now looks like P to the D M prime. If M prime is 1, then you're done. If M prime is greater than 1, which means that this is also not a P group, then you can repeat the argument and construct another subgroup H prime, and this subgroup H prime also has, so the subgroup H prime has cardinality which is again of the same form, which is the power of P is still the same, and the number M is now the number M dash, or rather M double dash in this case. Okay, so let's call it M double dash. Now if M double dash is 1, which means if H double prime is a P group, then again we are done. Okay, so now again it's now a question of just repeating the argument again and again. So observe, if M double dash is 1, then we are done. If M double dash equals 1, then the Sylow group you're looking for is just H double prime. You're done. Else repeat the argument again. Okay. Okay, so else would mean M double dash is also positive, strictly bigger than 1, you can construct another guy, and so on. So observe that this sequence of subgroups that we are constructing, they all have the following property, that they all have cardinalities of the form P power D into something, that P power D is the same throughout, and these numbers M, M dash, M double dash, M triple dash are all M is strictly bigger than this, is strictly bigger than this, is strictly bigger than this, and so on. They're all at least 1, of course. Okay, why is this strict inequality? Is because at every step you have a proper subgroup, right? So the cardinality of G is strictly bigger than the cardinality of H prime, which means that since P power D factor is the same, M had better be bigger than M prime. Okay, so I construct such a strictly descending chain, but all of them are at least 1, right? So this means that the process has to stop somewhere. You can't keep going on forever. The process has to stop. And at some point it stops, you have to reach 1, which means that there is some subgroup at some dash 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 has cardinality P power D into the corresponding M dash 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 had better be 1. Okay, so in other words, its cardinality is P power D. Okay, so you can't keep going on and on here. At some point the process has to stop, which means that you must have reached a P group. Okay, and that's really the proof of the theorem. Okay, so this is proof complete. Okay, so if you have seen maybe the proof of Sylow's theorem from prior courses and so on, this is it looks slightly different, but the proof has been arranged in this manner primarily to focus on the fact that Sylow's theorem itself is actually just a consequence of a statement about the existence of fixed point free action. So this is really what underlies Sylow's theorem. That's what's going on in the background. Okay, now so I hope you will sort of look through this proof again and try to understand the basic idea here. It's a rather simple idea that at every step, if you have a P group, you're done. If it's not a P group, you can construct a fixed point free action, take one of the orbits in that action, which is not divisible by P, the cardinality not divisible by P, and the stabilizer of an element there will give you a proper subgroup, and keep going on and on and on. At some point that stabilizer will have to become a P group. Okay, otherwise this process goes on forever, which is a contradiction. Okay, now that's an interesting consequence of proposition B, but what is extremely interesting is that in fact the first Sylow theorem also implies proposition B. Okay, so we have proved one implication, but in fact one can show that you can now assume the statement of Sylow Theorem I and deduce proposition B from it. Okay, so I'm going to leave this as an exercise for you, but please do try this exercise. Show that Sylow Theorem I implies the statement of proposition B. Okay, so assume this statement and prove the other statement. Okay, so which means that, so what does proposition B state? If it's not a P group, then you should somehow construct a set X on which the group acts without fixed points. Okay, and to do that you have to use the Sylow subgroup now. Okay, so if G is given to be a non-P group, look at the P Sylow subgroup of that group and use the group and the subgroup to somehow construct this set X on which the group acts without fixed points. Okay, so it's a very interesting and useful exercise, and I hope you will try your hand at it.